Hello. I made a small, well, it wasn't really a small error. I made an error in my video about the wrong skin, and it needs to be corrected, for several reasons, and I'll explain where the error is and why it needs to be corrected. So uh, let's get this going here. And this is also a great lesson on why you should check everything. Now, in a previous video, I said that if you have two functions, two differentiable functions, u and v, then the claim I made was uh, that u and v, I should do this here, are linearly independent if and only if the Wronskian of u and v is not equal to 0. Now, technically speaking, and not equal to 0 identically. Now, when I said u and v, I was acting as if u and v, you only had the formula for the function. What I forgot to do, and I'll put this in red here, u and v are linearly independent, and I'll insert this in here, over some domain where both are non-zero. So over some domain, and let's say open interval a to b, where it's possible b could be a number or it could be infinity. And same for a. So I have to include the domain here. And this is what I'm getting at. The very first part where I said, suppose u and v are linearly dependent on this interval. Well, that means that since it's two functions, that v must be some constant multiple of u on this domain. So if you took the Wronskian, you took the Wronskian of u and v, that's the Wronskian of u and alpha u, which is the determinant of u, alpha u prime, alpha u prime. And it's an easy exercise to see that that's 0 identically. So that part there is no problem with. Here is where the issue is. The issue is right here. And this is where I think I'm going to do the fix. Now, there are textbooks that say, well, suppose u and v are sometimes they'll add the hypothesis that u and v are the I should say this. Sometimes the hypothesis that um, u and v are solutions to some differential equation where that's possibly a function of x is added. However, here's another fix that would possibly work. So suppose we have some interval where v does not vanish. That is, v of x is not equal to 0 for any x on that interval. So if you do that, then if you do the derivative of u divided by v, and then by the product, the quotient rule, and again, we're not allowing v is not equal to 0 anywhere on this interval. Once again, this is the minus Wronskian of v squared. And if the Wronskian is 0 on that interval, the derivative is 0. So what this means is that the derivative of u over v is equal to 0 on that given interval. So u over v is a constant on that given interval. Therefore, u is CV, which implies linearly dependent on that interval. And that's an important distinction. So what you'd have to do is you would have to, and now of course you could flip this upside down and say the same for u, but for this to work, you would need to have at least one of the functions be non-zero for all points on that interval. And here's why that's important. Now, and here's why that's important right here. So consider the following functions. Well, consider you have what function y1 is x squared, and function y2 is going to be x squared for x greater than or equal to 0, and minus x squared for x less than 0. Now notice y2 prime at 0 is 0, and y2 prime of x would be 2x for x greater than or equal to 0, and minus 2x for x less than 0. So if you take the Wronskian of these two functions, that's going to be, it's going to be, of course, x squared. And this will be, of course, y2. And then this is going to be 2x, and that's going to be y2 prime. And that's going to be x squared y2 prime minus y2 times 2x. Now, this function for x greater than 0, this is going, y2 prime is just 2x, so you get x squared times 2x minus, that's just going to be x squared times 2x, and that's 0. And for x less than 0, it's going to be x squared times minus 2x minus, let's see right here. So it's x squared times minus 2x minus minus x squared times 2x, which is also 0. So the Wronskian is identically 0. But it turns out on the interval, if you look at this whole interval, y1 and y2 are linearly independent. And let's take a look at why. So suppose let's look at alpha 1, y1 plus alpha 2, y2. And suppose you want this to be equal to 0 identically. Now try x equal 1. And for x equal 1, it's alpha 1 times 1 plus alpha 2 times 1. So alpha 1 plus alpha 2 is in fact 1. Now try x equal negative 1. Well, negative 1 squared is just 1, so you get alpha 1 times 1 plus negative 1. The negative of negative 1 squared is going to be a minus. So you get alpha 1 minus alpha 2 is 0. This equation here means that alpha 2 is alpha 1. And plugging this in, that means 2 alpha 1 is, see right here. Oop, that's a 0. Sorry about that. So 2 alpha 1 is 0. Alpha 1 is 0. Alpha 2 is 0. That's a definition of linearly independent. And if you look at the graph, the graph of y1, well, we know what that is. It's a parabola. y2 looks like this, but then does this. This is y2. y2 includes this part, and then this part. So in other words, on 0 to infinity, y1 is in fact y2, so that's linearly dependent. On negative infinity to 0, y1 is equal to negative y2. That's also linearly dependent. These two only become linearly independent when you look at this, at the whole interval from minus infinity to infinity. And what you can see what goes wrong here, because if let's say you do this sort of thing, no matter what you use for u and you for v, at x equals 0, this is undefined. So the interval that this conclusion works for, that a 0 derivative means this is constant, the two intervals this works for, the two largest intervals, are the 0 to infinity or minus infinity to 0. It does not detect that these are linearly independent from minus infinity to infinity. So that is why that works. And the other thing you can also conclude is that y1 and y2 are not both solutions to the same linear homogeneous second order DE. So that's a little correction I wanted to make. And I also wanted to talk about the, when I talked about linearly independent or linearly dependent, I was negligent to that, and that I did not point out that the interval is important. So that's what I wanted to do with this, and thanks for watching.